So we have gotten away then from section A. We're now in section B, which is reaction tendency. The main point or topic of last section was what? Oh, that weekend blur. Heat, okay, and usually we use the word enthalpy. Okay, entropies today. Okay, we use the word enthalpy. We did a handful of stuff. The first lesson we talked about sign convention, exo, endo. We talked about breaking bonds, forming bonds, all that kind of stuff. Okay, day 2 we talked about specific heat. Do you guys remember what specific heat is?
The change.
The change.
The change. Like on a phase diagram, it goes up and down.
Okay, sure. I'm more talking about like practicality, like what it means or what the definition
It
is.
requires a temperature of 1 gram of substance 1 degree Celsius.
How much energy it requires to essentially get a temperature change. Okay, and we said low specific heat means what?
It's easier to change.
Easier to change it, okay. Yeah, I guess I understand why you're saying easier to change it, because we could say go up or go down equivalent.
Yeah.
Does that make sense? Normally I just say, I always tend to just use the going up. Like I'll say, something with a low specific heat takes a lot of energy, or takes a little bit of energy to cause the temperature to raise or to heat up. Okay? But technically it goes both ways. So, all right, high specific heat means what?
The opposite.
Yes.
It takes more energy to change it.
Takes more energy to see a temperature change. So a lot of energy goes in, but only a small temperature change will appear. Cool? Okay, then we did the calorimeter equation. Q equals mCSP change in T. Okay, and then after that, we did our enthalpy of reaction, products minus reactants. Where did we look to get those values? The table in our book, yep, the big mega table. And those were enthalpy of formation values. Why were most of those formation values negative?
Because the bond becomes stable, which is less energy.
Yep, they bond to become stable, which is low energy, and we know low energy usually is going to be the result of energy leaving, and we know that that's why we see a negative H, because negative H tells us what? Lost energy. Okay, cool. And then Thursday, Friday, Hess's law was just another way of doing the enthalpy of reaction, where we kind of did that puzzle, all right? We manipulated some equations, and yada, yada, yada. Got her done. So, today, a little bit of review. Oh, I must have to turn this on. Oh, there's music playing. Wow, I think that music was playing the whole entire weekend. 'Cause I didn't turn that on this morning. Oops.
The classroom doesn't have anybody.
Oh, it doesn't make any noise. Oh, there you go.
Ooh, I don't like that.
Wait, you can't even see anything. Oh, no wonder. Going too fast. There you go.
Wow.
Okay, so just quickly review here. Oops. We should remember that breaking bonds, what? Requires energy. So bonded atoms tend to have low energy and are more stable. Okay, why can you make this distinction from this statement?
Because you need the energy to have it.
Say it again.
Needed the energy to have it.
Okay. So breaking bonds requires energy. So if I were to have something combined and then break the bonds, you're going to have higher energy left over, right? Which then you can make the distinction that if it stayed together, you would be lower energy and more what? Stable. Okay? then, if you remember, we spent a significant time talking about chemical reactions. All chemical reactions have 3 steps to them. What are those 3 steps?
Bonds are broken, bonds are formed.
What's the in-between step? You got the beginning and the ending. Bonds break at the beginning, bonds form at the end. What's the middle step? Quiet over here. Care to chime in, anybody? In order for bonds to be formed, don't those atoms need to get close to each other?
Okay. Yes.
Intermolecular forces.
Just say it random.
Well, no, that's relevant.
Yeah.
Because how else would they get together if there were forces?
Sure, but the intermolecular forces deals with neighboring atoms. This is like the actual chemical bonds themselves.
So intron?
Yeah. So bonds break. Let me put this up since it has been a couple days and we're a little sleepy today. Okay, these guys have bonds that are going to be what?
They're going to be broken.
And this is going to be the bond forming. In between, right, when these guys' bonds break, I just got a whole bunch of hydrogen and oxygens just flying around, right? Those hydrogen and oxygens must rearrange in order to form the new bonds. So, bonds break, atoms rearrange, bonds form. There they are. Do you guys not remember me saying rearranging atoms?
For some reason, that
A little bit.
I mean, I didn't focus on it because I really was more important to know that bonds breaking than bonds forming. You're right, that. I probably didn't spend a ton of time talking about that middle
it was
process.
just kind of a bit of a fun.
Okay. Then we talked about endo. Endo means what?
Sort of.
Coming in. So what's probably true about an endothermic reaction? More energy to break bonds or more energy forming bonds? Breaking. Because we know breaking is energy coming in, forming is energy going out. So, endothermic process means that more energy is coming in than going out, so my overall net energy transfer is going to be coming in, correct? Making it endothermic. This is where we said strong bonds are going to be broken, which requires a lot of energy. So these are strong bonds, but what does that tell you about the energy associated with the strong bonds? Do you remember that? Strong bonds means what for energy? Low. It's kind of, you know, if you think about it conceptually, it should make sense, but right off the bat, if you don't really think too deeply about it, you might mess that up. Okay? So, strong bonds take a lot of energy to break. Weak bonds do not give off a lot of energy, and that's why you have an endothermic reaction. And I'll summarize all this in a little bit. Okay, you remember this little visual? Strong bonds, low energy, stable bonds. Takes a lot of energy going in, okay, and little energy going out in the formation. So you see an overall gain in energy, and that's why your products are technically less stable than your reactants. And the only way to get this to actually react is to put in a lot of energy. Okay, we can do a products minus reactants, and you will see that we are going to get a positive number. Okay, exo is the opposite. These are weak bonds. And my products are strong bonds. So, weak bonds don't take a lot of energy, so little goes in and a lot goes out, giving us an exothermic reaction. More leaving than coming in. And we look at this little energy diagram. Okay, before I get to entropy, I want to make sure you understand something. I'm going to give you a little chart, because you need to be able to know strong bonds, weak bonds. I want you to write this in somewhere. Let's start off by saying energy associated with these guys. Do strong bonds have high energy or low energy? Low. Weak bonds? High energy. Let's talk about breaking these bonds. Okay? Do strong bonds, are they easy to break or hard to break? Now, when we're talking about breaking bonds, we're talking about requiring energy, right? So we could say to break a strong bond, it requires a lot of energy. Does that make sense? Weak bonds, easy to break. If they're easy to break, it don't take a whole lot of energy to break them. Right? I'm going to just kind of put a little line here to separate breaking versus forming. If you're forming a strong bond, remember forming bonds does what? Releases energy. If you're forming a strong bond, is it going to release a little bit of energy or a lot of energy? A lot. Now, why is that? Conceptualize that for me. Why would a strong bond release a lot of energy in order to get a strong bond?
It's gotta be low energy.
In order to get low energy, you got to get rid of a lot of energy in the formation of it. So, what could you say about weak bonds forming? I want you to be able to know this because if I go from strong bonds to weak bonds, is it exo or endo? With me, Rachel? What is it? Got endo, got an exo. Someone break the tie? Endo. Remember, low energy to high energy. If I started with low, and I went to high, what is it? Endo. And I can flip that and say if I start with weak bonds and go to form strong bonds, I'm going from high energy to low energy, and what's happening? Energy is getting released.
Oh, yeah, that way.
All right. Entropy. Not to be confused with enthalpy. The measure of the randomness, aka disorder of a system. So, if I have high entropy, what is true? Okay, that's a good. It probably has high energy. What did you say? More randomness. That's true. You could also say not very ordered, right? So if I have high entropy, it's less ordered or highly disordered, and a lot of times you're going to see high energy, like Rachel said. All right, the second law of thermodynamics, also known as the law of entropy. Here's what your notes say. Okay, it says exactly that. Do you guys remember the exact definition of the second law? This is kind of in the form of energy, because since we're talking about energy. You guys remember it?
Is it the matter energy can't be created?
That's the first law. Yep. The second law is all processes go to a higher state of disorder, or they go from order to disorder. That's the entropy law. Okay? When we're talking about going from order to disorder in the terms of energy, it would make more sense that when we're doing an energy change, we always lose some usable energy. We cannot completely convert, and you maybe have heard this or remember this from physical science, there's no such thing as a 100% efficient machine because of this law. We can get to 98% efficient, but we can't get to 100% efficient because there's always energy lost in the form that we do not desire it. So, does this make sense? What do you think those three pictures are trying to solve? Liquid and gas. This should make sense. Solid, liquid, gas. Which of the three is more ordered? Solid. So it would have the least entropy. Which of the three has most energy? Gas. So you can make the distinction that usually the more energy you have, the more what it is. Fill in the blank. The more energy something has, the more it is disordered. Right? All right, I think this is actually from the next lesson. Okay, flip the page. Yeah. So, since there's not that many people here, we will stop here. I'd like to keep going a little bit because the next lesson's a little bit longer, but we don't have a lot of people here. We'll stop here, let you guys do some homework, maybe study a little bit so that you're not doing so much studying before your test on Thursday. What's that? Yep.